So hi, my name is Caelan Garrett. We're going to talk about task and motion planning today. And namely, we're going to focus on trying to describe planning using a variety of different representations. So including ones that have substantial geometry, discrete aspects that commonly are seen in like AI planning, as well as probabilistic representations and kind of learned representations. Oops, sorry, my mouse is gone. The Zoom recording kind of dialogue went up and I think it froze my mouse. Interesting. Oh, okay. All right, does that look good? Sounds good. All right. So we're interested in general in enabling robots to be able to perform interesting and intelligent behaviors in semi-structured human environments where some of the layout is known, as in you might know roughly the geometry of a room and maybe the objects that could be in it, but you don't know exactly their initial state and their properties. And so this would be something like a household environment, as shown here in Boston Dynamics, or maybe even like a food preparation environment where the orders that are coming in change constantly. Somewhat more structured, but also similar are warehouse environments and of course, construction environments. And really what we want out of our robot is the ability to perceive these scenes, deal with as much unstructured elements as possible, but still again, act intelligently. Ultimately, what this looks like in a solution is a generic policy that's able to map the robot's observations to what it should do next. And of course, this looks like this nice little feedback loop with our robot over here, where it's receiving observations in the forms of O's from the world. It's thinking in its head via some representation, and then it's acting on that world itself. And again, we want to be able to actually use this single policy and generalize aggressively. We want to be able to deal with as much variability in the world as possible, all using the exact same solution. In general, for more complicated environments like a room, this requires chaining together different types of ways the robot can act in the world. So not just moving by itself, but moving and picking several different entities possibly, and also performing non-prehensile manipulation potentially. And so in order to do this, it naturally seems like the form of the solution should have this kind of baked in, and that the robot should be able to reason about these different types of action modalities in its head, and then how to actually combine them in order to be able to complete the task. And so this really is like a very nice fit for model-based planning, as opposed to maybe just like a direct feed-forward policy. So here's an example of one of the tasks we'd like to do. So here, the goal is for the robot to prepare dinner for a human, which requires that the cup with liquid be served to the human, and the block, which you can imagine represents a vegetable, such as broccoli, to be served as well. And so the robot's just told this goal state, and so in its head, it actually has to figure out how to achieve this by not only discerning that it should actually cook the broccoli, but also finding geometrically feasible configurations for both of these objects on the plate. And so really here, what we're seeing the robot being able to actually not only just reason about the discrete properties of the state of the block, but also the geometric properties of trying to be collision-free and upright and on the plate. Here's another example where the goal here is for the robot to detect the spam that starts in the bottom drawer, and it's able to use its geometric model of the world to understand that in order to be able to view the spam, it has to be unoccluded, and that the top drawer occludes it, and then actually furthermore, that the sugar canister on the top drawer needs to be moved, otherwise it would actually collide with the cabinet or with the surface of the kitchen when closed. And so here, really, the geometry is critical for the robot making actually intelligent decisions to be able to rectify this. And finally, as a slightly different example, here's a problem where the robot is told a structure to build, but not how to build it, both in terms of the sequence and in terms of how it actually can do it in a collision-free way. And so the goal of the planning algorithm is to reason about these constraints together in order to be able to actually find a full motion plan for these gantry-mounted arms to build the structure. And planning here actually is quite significant and does take about an hour, but fabrication takes a couple days. One big topic for discussion in general has been like, where does this model come from if you buy into model-based planning? And I'd argue that we want to take kind of a hybrid approach to this, that we want to use engineering when we actually know components of the system quite well. For example, we know things like kinematics of the robot quite well, that we have actually, someone has built these robots and has a spec for them. So there's no real need to re-engineer that. Lots of geometric operations we can do quite well. Maybe the entities that we're operating on, we don't understand as well, but in general, we want to be able to use these ideas when they actually are quite accurate. But at the same time, of course, we don't want to be kind of reliant on them overly. They'd like to be able to also address situations where we don't actually understand what's going on as well as we'd like. And so maybe an example of this would be if we're trying to characterize the set of good pores and scoops for a robot, this actually maybe is a easier task for learning than to try to directly engineer this. But ultimately, we'd like to be able to actually combine all of these elements together. And so one advantage of using this model-based approach is that you can actually flexibly mix and match different models, like submodels, when best applicable to model the various ongoing constraints. And ultimately, engineering does actually add the bias that kind of influences the solution, but it's a mixed bag in that the bias makes the learning problem much, much easier. It does actually maybe possibly restrict the set of solutions you have because it injects human priors, but you can do a lot of interesting and complicated stuff because you've made learning much, much easier. So here's an example of trying to combine both learned models and engineered models. Here, the goal is to prepare coffee. And to do this, you need to, of course, dump the dried chickpeas into the white bowl and also scoop and pour these little red particles in there as well. And so what you're seeing there is really a combination of both using an engineered and learned model, in that the learning is in total control of trying to understand the effects of pouring and scooping, but moving while avoiding collision, and picking and placing are things where you can use just classical traditional robotic engineering. In general, where I like to stand in the scheme of robotic problems is starting here, where even actually moving without colliding is quite complicated, but we'd like to be able to eventually operate in a very, very limited, or with very few assumptions about the world itself. And so we'd like to be able to not just be able to move around, pick and drop, pick and place, but we'd like to be able to do arbitrary manipulation where we don't know what's on the world at all. And so this involves actually, again, extending out of pick and place to deal with less precise skills, dealing in the real world with stochastic actions, where you, for example, if you put something down, there's always a little bit of error in terms of its ultimate placement, dealing with occlusion and partial observability in general, and then ultimately dealing with the world in the most unstructured way possible where you don't know what's in it. We're going to start a little bit closer to pick and place though, but we'll touch on a couple things that move towards this more general goal. The key thing that algorithmically that I've been able to do is to try to facilitate this goal for model-based planning with hybrid models, is to find a framework that actually allows you to plug and play different representations for different constraints that are involved. And then not only just providing this framework, but also efficient algorithms that actually can use it to solve complicated tasks. The key workhorse in this, as I'll say in a second, will be to try to extend existing AI planning to allow for external procedures, such as samplers, to be specified in the form of streams. At least that's our name of it. And really what this allows you to do is that you can actually, for different individual constraints that are relevant for a planning model, you can plug in geometric operations that generate values that test, or that satisfy the constraints and also test that they're satisfied, but also learn values. So you can actually have generically something that's able to take in the constraints and the free parameters, and using maybe a grasp generator, sample grasp values that have the property of being a stable grasp. And so this framework is intended to be general, and it will actually allow us to do most of, well, at least attempt to do a lot of what we're trying to accomplish in terms of broadening the scope of robotics. So this includes both just task and motion planning, but also trying to incorporate and learn values, deal with probabilistic values, so maybe operating on distributions over values instead of individual entities, and also eventually moving a little bit closer towards dealing with values that we don't understand well at all, but still actually incorporating them in the same model-based framework, where we're able to use a combination of planning, both when we understand what's going on and when we don't understand what's going on collaboratively. So we'll start with task and motion planning. So in task and motion planning, really the goal is to try to be able to kind of extend motion planning by finding plans for a robot that involve moving with different operational constraints. And so this kind of goes beyond just one motion, but also deals with chaining together different motions that impose different constraints and have different values governing those constraints. For example, in the state, traditionally, we have both the state of the object and the objects in the robot in the world. So the configuration of the robot, the different values for objects in the world, including their poses, and if they're articulated, maybe their joint angles themselves, but also discrete notions in terms of contact and other kind of inferred properties. And so while the robot's actually moving and holding something, there's this constraint that the robot has constrained to keep the object that's being held in a stable grasp, which governs the set of things the robot can do safely. And so because the object actually, because my cold brew coffee extends the volume of the robot, it renders moving close to the table unsafe because it's attached. And really what we're looking for in terms of solving these problems is a ultimately continuous sequence of motions of the robot, but also a sequence of different action types that it's going to actually perform. So again, moving while the hand is free, picking, placing, moving while it's holding something, and then also other potential actions that go beyond prehensile pick and place. And again, for the task constraints, that we have things like grasps and stable placements that the robot should maintain as it performs its behaviors. One example of a TAMP problem specification. Also, actually, Chris, what's the target end time? Is it maybe 10 more minutes? Okay.
Yeah, I think we have.
I forget exactly when we started on the.
We started 10, 15 minutes late. So I think you should have correspondingly that much time.
All right.
Yeah. Started at cool. 1925. Yeah.
All right, sounds good. Yeah, so the form of a solution in a TAMP problem looks like this. Essentially, you're given as an input, of course, the start state and some goal spec, which can be translated as just a set of states. And you'd like to be able to find through planning, a sequence of operations to actually perform. Again, in this very simple example, this involves moving while free, moving while holding, and picking and placing. This actually will induce a set of free parameters, which are shown in color here, where we have free parameters for the configuration of the robot for each pick and place, the grasp chosen in the placement, and the motions, of course. And these parameters should actually satisfy a set of constraints. And so here visualized are constraints for collision-free motion, C-free, for the kinematic switches when performing each pick and place, the constraints for representing that the grasps and placements chosen are stable, that they will not move too much while the robot's going. And an ultimate solution basically is an assignment to all these values in color that satisfies these constraints. And so this whole problem really is a constraint satisfaction problem conditioned on finding the skeleton of operations that the robot will actually perform. You can approach this in many different ways. And so if you have this constraint network, you can reduce it basically to a mathematical program. So you can say all these constraints are into some sort of very complicated non-convex optimization routine, still well formulated, and try to directly address them. Or you can use other techniques such as sampling, which is something that's a little bit closer to what I traditionally use. I think critically in TAMP, that for at least for most like kind of classical TAMP work, really the interplay of discrete and continuous nature is critical. And one of the big realizations for all of this is that oftentimes there are complicated and difficult to satisfy constraints that actually restrict what you can do, continuous constraints that restrict what you can do on a discrete level. And so these are things like obstruction and occlusion. For example, on the picture on the right, the goal might be to pour the contents of the blue cup into the bowl, but because of its position and how it's situated with respect to the robot, and because the green block's in the way, the robot has to automatically infer that in order to be able to stably pick up the cup, we have to relocate the green block somewhere else. And so really here, just directly trying to pick and pour the blue cup is not viable at all. And so the robot must use its geometric model of the world in order to discern that the green block is the kind of affecting object. And so here, really central to a lot of TAMP is that you can't just strictly reason about these types of interactions in a hierarchical way. That you can't just do, for example, task planning, then motion planning, because these constraints actually restrict what you can do on a task level. And so trying to be able to jointly reason about all of these things at once is, I think, critical to the heart of this kind of behavior. Here's another example. Here, the goal is for the span, which starts in the top drawer to be in the top left cabinet. In order to do this, the robot has to be able to be collision-free. So that requires actually opening the door, of course. So the robot does so. It also is able to, or also, because the top left cabinet's actually quite tall, the robot can't naturally reach it and perform a top grasp. And so the robot's able to use its model, though, of various grasps and kinematics to say that the current grasp that I'd like to achieve, which would be a top grasp, is insufficient for achieving this. And so it's able to then plan to place the object on the counter in order to switch the grasp and then ultimately place it into the cabinet. And again, this involves a couple complicated, constraints, but we're able to actually enable the robot to plan this behavior just by giving it this like rich model of geometry and the discrete elements of the task. And so by automatically propagating these, it's able to understand this and then plan accordingly. And these constraints can be even more exotic and involve structural constraints. For example, when trying to 3D print an object in space. Our key contribution is a representation for trying to induce this behavior that allows us to, again, mix and match different types of constraint or representations of the problem all in one planning model. And so far, we've shown mostly mixing geometric and discrete aspects of the problem, but we'll be able to show others as well, including dealing with distributions of values and dealing with values that we don't actually have good models for. And there's a lot of details in terms of the kind of operation of this framework, but really the key thing is the representational aspect, which is to take an existing AI planning framework, PVL, and extend it first to deal with continuous values, and then second to deal with kind of arbitrary tests that are formulated in terms of like a Python function that can do things like test satisfaction constraints and also sample values that actually are satisficers of those constraints. And we have plenty of algorithms that can deal with this framework generically, but really the key thing as a first order contribution is the representation. And I'll go in briefly what this representation looks like. I won't talk about the algorithm so much today, but really, again, it's the representational part that is the crux of all this. So here is a very, very simple example that is actually quite close to all the ones I've shown you before in terms of its complexity, but kind of highlights the form of this representation. So here's a 2D pick and place domain with two objects, A and B, and a robot, which is a basically top grass vacuum gripper in this example. The states of all these values are just XY positions. And one example problem that we'd like to solve within this domain is to have block A be on the red region, contained fully on the red region. And really here, critically showing off the interplay of geometry and discrete aspects, block B intentionally obstructs all safe placements of A in that region and needs to be moved somehow. So here's one example of a solution. Note that although the kind of skeleton here, the discrete sequence of what to do is quite clear, there are implementing solutions to this problem because one of the free parameters is the placement of block B. So the robot needs to be able to find that skeleton, but also kind of resolve values for those variables. So when it's thinking about trying to extend the classic AI planning representations, which again are inherently purely discrete, we want to be able to maybe propose the fewest modifications as we can, but still have the level of expressiveness that is able to model the previous example. And so when describing what's going on, we can start to write down the initial state as 0, and also facts that the initial state satisfies. And so these really could be part of the state itself, but are just kind of static entities to describe, for example, properties of the values involved. So the fact that A is a block, B is a block, negative 7.55 is configuration of the robot, etc. And we can also write down the goal expression, which could be a quantified formula that looks for a pose for A that's within this red region. And eventually to get there, it will have to be collision free. And when, again, thinking about trying to extend this language, nothing really is surprising that describing an initial state and a goal specification is straightforward, but we'd like to be able to do it in a way that allows us to have these continuous values in play. And so again, each of the positions and configurations are effectively NumPy arrays when it comes down to it. We can start to describe also actions. So here we can write down in a strips-like format, classic moving and picking actions, where there are free parameters. And so for a move action, the free parameters are the initial configuration, the trajectory taken, and the end configuration. There are preconditions. So those involve not only the constraint that, for example, the robot has to be at configuration Q1 before it actually performs a move, but also constraints on the validity of the action parameters themselves. That if we want to define a legal motion, we should ensure that trajectory taken, T, actually moves between Q1 and Q2. And in a similar vein, we can describe picking and placing. And then finally for move, actually, the effects are to update the configuration of the robot to be at Q2 and then delete the fact that the robot is at Q1. When describing picking, we could do a very similar thing where we can have constraints on the parameter values, such as this kinematic constraint kin, conditions on the initial state that is legal to execute this pick action. So again, constraints on the initial configuration and the pose, and as well effects on the results. So here, after the robot picks something, it's now at a grasp, it's no longer placed, and the hand's no longer empty. So if we were given values for these variables and assertions that they satisfied constraints of interest, this problem would be quite easy actually, and that would be just basically a finite graph search. That if you have all the relevant configurations of interest, all the placements, then just doing a breadth first search in state space is sufficient. But really critically, this is not what you're given. The robot has to infer these things automatically. Namely, that although the initial state contains some values, such as the initial configuration of the robot and also the initial poses of the objects, the planner needs to find one placement for A within the red region, a collision-free placement for B, a grasp for both A and B to do the kinematic switches, and also configurations that are accordingly able to actually do the switches. And so the key thing representationally is that we need to be able to generate these values. And so we need to be able to, for example, sample different values. When trying to make samplers that do, for example, find placements of an object, we already have some headaches in that the placement constraint is actually lower dimensional than the spaces of pose. So here, if we're trying to, for example, sample SE3 for a pose placement of an object, if we do it just kind of blindly, uniformly over some bounded subset, there's zero probability that we'll actually find one that lands on the top of the surface. So we already have to be able to kind of inject some geometric knowledge of the space in order to find values that satisfy this constraint. Additionally, we don't just want to be able to satisfy one constraint, we want to be able to satisfy a couple in conjunction. For example, we want to find placements, but also find robot configurations that are able to actually facilitate placing, which requires, for example, performing inverse kinematics. But what we can show is that by allowing these samplers to have inputs, to have arguments, we can actually condition on existing values and then also use that information to generate future values that satisfy an additional constraint. So we can find combinations of a placement and robot configurations and ultimately a continuous motion that are able to be first a placement, have a kinematic solution, and also facilitate collision-free motion. And we could do this generically in the form of a DAG, essentially. The way that we actually try to kind of formalize these samplers is to actually use the language of planning itself, that we want to be able to describe the inputs and outputs, and we can use logic to do so. That we can describe conditions on the set of legal inputs. For example, the inputs to a motion planner should be configurations, not maybe an image or a word. And also describe properties of all the values that come out. So all the values that are the output of a placement sampler, for instance, should be kind of asserted that all the values coming out are stable placements in some target region for which it was sampled. And basically this input-output spec allows us to model all of these interesting sampling operations that then could be automatically used in conjunction by a planner to find values that satisfy all these constraints. And so we can do this for the sampling placements in a region, for inverse kinematics, and for motion planning. And really what the key takeaway of this is that this abstraction that allows us to generically define tests and samplers in a planning domain basically allows us to be very, very flexible in terms of the types of constraints we use and also the types of values that come in that. We have plenty of algorithms that, again, address this problem class, but we're not going to go into them today. I'll just skip through. And they're fairly fast, but you have to interpret the table. What we're able to do actually is we're able to not only model just pre and sal pick and place, we're able to actually learn samplers that are able to model operations like pouring from data directly. And so we can basically define one of these constraints as a test G, that the control values actually are likely to have a good score. So here, scoring is just the particles that are in the bowl when pouring. And then also we're able to then take that constraint and then sample these values directly. And so the implementation of these constraints and samplers, again, can be very generic, but allows us to learn skills like pouring and scooping without worrying too much about how to actually combine them with other operations, because we're able to define this model that allows us to generically use different implementations for different constraints. So ultimately, again, getting back to the start, so we'd like to be able to work in the real world, which requires being able to deal with partial observability, which I think is maybe most challenging in particular. And so we can use this planning model in a policy, basically in a traditional state estimation, planning, and control loop, and use replanning in order to facilitate real world behavior in uncertain worlds. Let's see. In order to be able to deal with uncertainty, we need to basically introduce distributions. We can't just have a deterministic planning problem or even just a estimation problem. But we're able to actually show that rather than necessarily just defining samplers that act on individual placements, that we can define them over distributions of placements.
Hey, Caelan, 1 minute. Would you be able to wrap up in the next couple minutes? I think we're a bit over time.
Yeah. I plan way too much, I think, but yes. Essentially, we're able to model the whole belief process itself, including trying to find detections of like poses of objects, and then define sampling operations that perform probabilistic inference operations. So this involves basically sampling different likely observations and also computing posteriors. And this allows us to start to have the robot be able to use planning over distributions to facilitate information gathering, where it will actually intentionally open drawers in order to find values because it has high uncertainty initially, but also resolves it via observing the world. And then finally, we're able to actually deal with scenarios in which we don't have models for any of the objects involved by using neural network samplers, essentially, to generate values instead of where you would traditionally have a classical fully known object model graph generator, allowing us to deal in very unstructured environments. But again, really the takeaway, I think, is trying to, by enabling a model that's very hybrid, that's able to reason first about discrete and continuous values simultaneously, but then extend to deal with distributions over these values, and also values or entities that we don't have great models for, we're able to kind of combine all these elements into a single planning framework and do a very wide range of planning and demonstrate a wide range of behaviors. And so really trying to, I think ultimately the takeaway is by being able to be hybrid in the representations that you can reason about, you're able to extend to a wide range of circumstances. All right, thank you everybody. Here are some bloopers / highlights, depending on how you view them. I'll take any questions. Oops.
I think in the interest of time, we might want to take the questions via chat, if that's okay with you, Caelan. And then
that's fine.
We'll move on to Joe. Does that sound good? So
yeah.
So